next speaker is Laurent Roussel, FEI company, and he's going to give a talk entitled Expanding Boundaries of High Resolution 3D Characterization Analysis using DualBeams.
Many thanks, Jakob, and again I'd like to thank Jakob and Riso for, let's say, hosting this event and for the hospitality. So here I'm going to take, I would say, almost the complete opposite side of the previous presentation and mainly focus here on, you could say, the acquisition of three-dimensional information using DualBeams. As an introduction, actually, I'm going to be pretty short on, let's say, the general process because it's been already described this morning. Not that it is so much different whether when you use FEI systems. So just as a quick reminder, whenever I'm referring to DualBeam, I'm obviously referring to a system that has an SEM and FIB-SEM on the same instrument with the two beams meeting at one point. And all DualBeams will always have the same geometry in the sense that the angle between the two columns is going to stay constant at 52 degrees. So which also helps, let's say, having kind of uniform automation across instruments. Then, like we've seen already this morning, says that the general acquisition is pretty much standard in a sense that, let's say, there's going to be a first phase when it is about defining what one expects in terms of dimensions, how the sample should be prepared, etc. Then comes a whole block of automated operation where the FIB is going to align, let's say, prepare a surface for then data to be acquired, and then this data we've already seen this morning, we're going to see even more now, but different types of information can be actually acquired. Then once a full data set is acquired, comes, let's say, whatever happens, let's say, offline the DualBeam, and this is, let's say, the next step. Well, what do I do to get meaningful data? To be very specific, I have to say, as far as FEI is concerned, there is still a huge effort in this area because it's a pretty open area in the sense that there's, I have to admit, probably more ideas right now on the table than what can be, let's say, truly achieved in terms of products that we can deliver. But it doesn't mean that, let's say, we're also completely forgetting about that. This is also typically where we like to connect with users, simply also because what happens here will also very much depend on the kind of application that we will be considering. Obviously, the needs of fuel cells will be somewhat different than the one of biology, just to give two examples. So now, let's say, talking quickly about the evolution of this technique, we typically call this technique slice and view in FEI. It's something that is existing actually for really a couple of years. I would even fail to put a real date on this, but the first slice and view technique came actually pretty shortly after the introduction of first DualBeams. Let's say from there, a number of things have happened since. You could say more recently it's been, first of all, about really having, let's say, an even more robust and friendly automation to produce those data, and rather you could say shift the problem of, let's say, working on the data rather on how to acquire them, and then about also expanding the amount of information that can be obtained, and that is not only SEM images, but let's say we've seen already, let's say, chemical data, crystallographic data. Well, data from a wider category of samples as well, and not only, let's say, hard materials. And that alone has already created, let's say, more constraints in the sense that you can just take it for granted that whatever we knew about, let's say, the generic slice and view, we're just going to put a new detector, and right away my automation is going to work. So it's simply not true. So this is why actually quite a lot of work is happening also for each individual techniques to just take the needs and work on them to have, let's say, meaningful data. Then, let's say I'm going to expand, let's say, a little bit on each of these points, let's say, throughout the presentation, but let's say the bigger chunk of the presentation I'm actually going to concentrate on, let's say, more recent work that was done around the slicing and view techniques in DualBeams, and especially in the light of higher resolution getting towards isotropic voxels and larger volumes. Just to give an example, so this is the typical kind of automation that one would find nowadays in a DualBeam, with one example that was taken out of, let's say, of life science, actually red blood cells, and where one would typically, let's say, look at a top-down image like this with a focus line beam just to define the area that one would want to analyze. And then, well, we'd say just press the play button and just acquire all the data, which would then display also here in the automation. So here you can really go through each individual slices that you can acquire with the DualBeam. In terms of volume, also just to set expectations. So here, I mean, that's a really very classic volume in terms of, say, time to results. So typically 20 by 20 by 10 microns. And also here, let's say the image resolution. Why here was chosen to be 2000 pixels by 1700 approximately, meaning let's say we get something like a 6 nanometer per pixel, let's say within the image, and working here again locally backscatter imaging. And well, together with this, then there is also first of all the stack of slices that have been acquired, and then together with this also the 3D rendering of the 3D of the cells. So again, here that is just more an introduction. Now, moving, I would say, closer, let's say, to the topic of this symposium. Well, we will also get some time to see, let's say, some of these fuel cell electrodes in our reports. And well, this is just one, again, classic example without, let's say, any, let's say, with the very routine automation, 10 by 10 by 5 micron, with, let's say, good contrast, let's say, between the different phases and porosities that are visible, and then here the rendering related to the porosities. I have to say here this is work that was done by also, you could say, a DualBeam specialist, but not a fuel cell specialist. So also here I'd be at a loss a little bit to comment, let's say, on the real quality of, let's say, the construction. That's also more something let's say, to be discussed with users. And then, let's say, like I said, moving, let's say, from the traditional SEM images, there's now definitely the possibilities also to, let's say, deal with other types of problems that, let's say, we encounter. I have to say more and more going to a wider range of materials, starting, let's say, with those materials which are actually sensitive to the electron or the ion beam, and where it becomes actually possible to just cool the sample to typically say minus 150 degrees, and actually get, let's say, first of all, contrasted SEM images from those samples. So that's, let's say, typically it's a combination of hard soft materials, rubber filled with, let's say, hard materials, typically like silica, and which can then also follow the same process of cutting and gathering three-dimensional data for further construction. Moving, let's say, further in the amount of data that can be acquired, let's say, like was mentioned already this morning, definitely the possibility nowadays to also include chemical analysis or crystallographic analysis with EBS and EBS respectively. And the idea, again, as far as DualBeam is concerned, is to have, first of all, let's say, unified automation interface so that also, let's say, there's minimum, say, effort from a user point of view just to acquire the data, and also, let's say, having some kind of a universal way of connecting well, different technologies which are not within FEI, cameras in particular, to the automation, again, for using the specificities of each of the different vendors' cameras. In particular, this has proven extremely useful, let's say, for also managing the transition to fast cameras and detectors lately. We've seen already, for example, that collecting data can be actually quite time-consuming, and every bit that can be gained is obviously plus. Then, also, and like mentioned in the previous slide, it's actually quite important, let's say, that each of the interface is customized to the need of the application. And specifically when we're going to talk of chemical data acquisition or crystallographic data acquisition, say the needs are not going to be the same in terms of sample preparation, but also in terms of the position of the sample for doing the analysis. This will also impact the result, not necessarily their quality, because there could be different positions that one could think of, whether it's actually the speed that will matter in the acquisition, or let's say the spatial resolution, etc. So here there is also choices to be made, and also about let's say the output of the data. Very quick also here some examples related to 3D chemical analysis. First, where on the top you let's say have the raw data that have been acquired with the EDS, and then bottom that's already the 3D reconstruction. That's at the moment a very crude reconstruction that was made based on the different maps that were collected in the process here, and each element has been actually isolated with a different color. So again, you could say from an automation point of view, this is something that works extremely well. It's robust enough that you can actually really work for tens of hours to collect data. It's already able to well cope with the low KB so that we can actually well reduce the interaction volume. But again, and knowing EDS, the interaction volume still remains a concern. Let's say at 5 kilovolt, we still have, let's say, tens of hundreds of nanometers of that comes from the depths, and which should be taken into account when generating the data. At this point, let's say, the not so meaningful to actually collect slices that only are at steps of 10 nanometer when your information comes from much deeper than that. So this is also, let's say, the reason why, let's say, as FEI, we've been trying to push, let's say, this kind of automation so that actually data sets could be generated. And the main idea being that one would generate really, well, collect all possible data without necessarily filtering them, which practically result in let's say, a pretty big amount of data. But then leave room, let's say, for users and whoever wants to well, get started with us on this to see how this data can be processed in order, let's say, to just improve on the raw representations of data. One example also here related to crystallographic data. Here I've chosen for a set which, well, I've seen actually come on the table pretty often, at least in terms of dimensions. It's not unusual that whenever wanting to do, let's say, crystallographic analysis on, especially on metals, in this case steel, well, one has to deal with fairly large grains, and the first thing that comes on the table is I need to do a reconstruction that actually deals with a pretty significant volume as far as DualBeam is concerned. So let's say this is definitely also something that is possible. I have to say I don't want to scare anyone with the time it took to acquire this, because that was still done at the time, I have to say, with a slow camera. So here actually this let's say, animation, it wasn't so much, let's say, the milling time that has been the bottleneck, but rather let's say the acquisition of the different patterns for the reconstruction. And well, then let's say put all what it takes in terms of sample positioning, clearance, etc., so that you can again get high quality data, which we actually get to see here, and especially, let's say, in this case, have a way that let's say the map are not do not show any shadowing effect, whether you talk of the very first maps all the way to the last maps. So again, here I'm talking really state-of-the-art technology. Now, let's say moving also about, let's say more recent needs that have been